Hi guys, welcome to a channel that affords you the opportunity to study at your own pace, time and place. I hope you are enjoying the videos that I'm giving you on this favorite channel of yours. If you are enjoying, the subscribe button is there for you to confirm. Simba kumshand, let's enjoy. Hi guys, welcome to another new topic this week where we'll be looking at Zener Diode. In our last video presentation, we looked at the light emitting diode as well as the optocoupler, and these were optoelectronic devices. As I said, circuit symbols or schematic symbols, applications, operation, construction of those optoelectronic devices must be at your fingertips. And our new topic is on Zener Diode. Guys, this is a very important topic in electronics, and you cannot sit for an exam on electronics 1 and you miss that, or you miss a question on Zener diodes. It is a very important device in electronics, and its major function is as a voltage regulator. Let's enjoy it. This is what you are expected to be able to do by the end of this video presentation. 1, you must be able to differentiate a Zener diode from an ordinary diode. It's a very important point. Number 2, you must be able to produce Zener diode characteristic curves and label its important parameters. That is very, very important as well. Then you must be able to draw the equivalent circuit of an ideal and a practical Zener diode, just like what we did on an ideal diode and a practical diode. Objective number 4, you must be able to describe the Zener diode as a voltage regulator under varying input and varying load, and to perform simple calculations. Guys, that I can say that is the most important objective which you must be able to do, and examiners like it. Then obviously must be able to describe Zener diode applications with the aid of circuit diagrams. Let us look at the introduction. What is a Zener diode? A Zener diode is a PN junction diode. Can you see the emphasis that is being put on PN junction, which means you must know the semiconductor basics. Otherwise, it will be difficult for you to proceed. It operates in the reverse breakdown region, in which our normal PN junction diode is not able to operate. But when it is forward biased, it simply functions as an ordinary PN junction diode, but rarely is it used in this forward biased condition. Why? Because it loses its voltage regulation, referencing capabilities, surge, clipping, as well as switching capabilities. So, for it to be able to achieve these capabilities, it is operated in its reverse biased condition. As I said, it is a PN junction and is normally or generally operated in its reverse breakdown region, and we are being given the voltage range of most Zener diodes. That's from 1.8 volts to 200 volts. Zener diode was discovered by a physicist by the name Carl Zener, and he investigated the breakdown phenomenon in a PN junction diode. Guys, as I said yesterday, some of you are not giving schematic symbols their due respect, and I am not happy. This is the most commonly used symbol of a Zener diode. Please take note of this and its direction. This is the ordinary anode that we know, but the Zener is no longer a straight line, and this is the cathode. This is another symbol for a Zener diode. We have simply removed this bent end of the other side, but the symbol for the anode is still the same. And we said this arrow, this shape of an arrow, shows the conventional flow of current, which is the same as conventional flow of volts. So make sure you know these two symbols by heart. Why is it important to know schematic symbols? Because sometimes you see these symbols used in a circuit, so you must be able to identify them. Forward and reverse biasing a Zener diode. We know this is the symbol of a Zener diode, the anode and the cathode. How do you tell whether this diode is forward biased or not? You simply you simply check if the positive of the applied voltage is connected to the anode, and if so, we know that the diode is forward biased. And because of the direction of this arrow, our current is going to flow in this direction, and we are calling it the forward current. This is a current limiting resistor, and we said when a diode is connected in this way, it operates as a normal PN junction diode. When it is reverse biased, as in this case, this is the cathode, this is the anode. The voltage across the Zener diode is called VZ, and please take note its polarity is now different from the voltage across the PN junction diode. This is the positive side and this is the negative side. So we say because the positive terminal is connected to the cathode and the negative terminal to the anode, our diode is reverse biased. Please take note of the direction of flow of current. It is in this direction when the Zener diode is reverse biased. And this is for you. The arrowhead shows the direction of conventional flow of current, which is the same as the direction of volts when the diode is forward biased. And in this direction, in this diagram, it is now totally different. Please, as I emphasized, take note of the reverse current. IR stands for reverse current, then the current limiting resistor R. So we are interested in Fig B than in Fig A. That slide is a recap of what you know. I'll rush through it. We are explaining forward biasing, and we are saying the anode is connected, the anode of the Zener diode is connected to the positive terminal of the DC source, direct current source, and the cathode to the negative terminal. And we are saying when forward biased, it behaves like a forward biased PN junction diode, but it is rarely used in this case, but it is operated in the reverse breakdown region, as the last statement shows. And when operated in the reverse breakdown region, that's when we have the voltage regulation function, which is the major function that we are going to dwell much on in this video or presentation. We are sliding deeper and deeper into the Zener diode. We are now looking at reverse breakdown. We said it is operated in the reverse breakdown region. This is the reverse breakdown region where reverse current is negative and also reverse voltage is negative. And we are concentrating on the parameter called reverse breakdown voltage, V subscriptive BR. BR stands for breakdown, while V stands for voltage, and this is the voltage. But the voltage from 0 in the negative direction to VR, we are calling it negative reverse voltage, and we are saying this is the minimum reverse voltage, which means we are defining this voltage. This is the minimum reverse voltage that causes a device to break down. What are we saying when we are saying the device is broken down? We are simply saying we now have an increase in reverse current, which is a substantial increase. It's actually our reverse current was a constant after initially increasing from 0 to this very small value. But when we get to breakdown voltage, we now have a substantial increase in reverse current. And when this happens, we say the Zener diode has gone into the breakdown region. And we are saying, as the curve illustrates, two things happen when we reach breakdown voltage. That is, the diode current increases drastically, as we can see, and the reverse voltage across the diode remains fairly constant. This is the breakdown reverse voltage. There is a very small increase in VR from there to there. That's the reason we are saying it has remained relatively constant, while there is a substantial increase in reverse current from there to there. More on reverse breakdown, as I said, deeper into the Zener diode. This Zener diode is reverse biased, as we can see, but please take note of the voltage across it. It is a positive voltage. This is a positive voltage. When the negative is there and positive there, which does not happen across a Zener diode, we say it is a negative voltage. It especially happens when it is across a capacitor, depending on the circuit connection. So we are saying this is a reverse biased diode. And we are saying VR remains almost constant over a range of current values. And this is the characteristic that is wanted for a voltage regulator. What is a voltage regulator? This is a circuit that is designed to maintain an output voltage at a relatively constant voltage, despite increase or decrease in supply voltage or variation in load current. So we are saying we don't want the output voltage to vary as the input voltage vary, or as the load output increases or decreases. So we are saying the forward current flows in this direction, or the reverse current flows in this direction when the diode is reverse biased. And there's this term which you must understand, because we've got a positive there and a negative there. We are saying the cathode is more positive than the anode. Thus, our diode is reversed. I can't keep on repeating myself. Go through that slide and see if it makes sense. I've gone through most of the points stated in that slide. In one of our previous lectures, we looked at the two types of breakdowns, Zener breakdown and Avalanche breakdown. We are repeating the two. Please, I beg you. These two types of breakdowns must be at your fingertips. This time I've included a diagram, and we are starting with the Zener breakdown. And we are saying this occurs when the applied reverse voltages produces a large electric field. A large electric field is developed across the PN junction diode. And we are saying its magnitude or its size causes a large force on valence electrons of atoms. Mind you, we've got atoms in the P type as well as atoms in the N type, and these atoms have got valence electrons, and valence electrons are least attracted to the nucleus. So because of the large force, they are going to escape from their parent atoms, and once they escape, they become free. They will be under the influence of the reverse applied voltage. So we are saying this is going to result in the creation of electron war pairs in large numbers, and this is going to cause a sudden increase in current. These are the detached electrons, and these are the detached. When an electron is detached, we know it leaves a hole. We are saying this reverse voltage, the negative repels electrons and the positive repels holes, and this is due to, we know, minority charge carriers. Remember, minority charge carriers, they flow when a diode is reverse biased. So the increase in the voltage results in a strong electric field which causes valence electrons to escape from their parent atoms. Once they escape, please, they become free. Avalanche breakdown is another type of breakdown which occurs in diodes, and this is caused by an increase in the applied reverse voltage, and this causes the acceleration of minority charge carriers and cause them to gain sufficient energy. Please take note that it is the collisions of the minority charge carriers against covalent bonds of the crystal structure of silicon or germanium. When that collision occurs, we are going to have some electrons breaking away from their parent atoms, and this is going to create electron hole pairs as shown. These electron hole pairs are then the new charge carriers we are referring to as the secondary particles. They are also going to be accelerated. Take note of acceleration, and they are going also to experience or to collide against the covalent bonds, generating again more electron hole pairs. These new electron hole pairs are going to be accelerated as well, and after collision they are going to generate again more electron hole pairs, and this is what we call carrier multiplication. So please, you must be able to compare and contrast avalanche breakdown and Zener breakdown. In Zener breakdown, there is no collision. Please take note, it is the electric field that causes the disruption of the bonds. This is the diagram showing avalanche breakdown, and as you can see, this due to high velocity, it is going to collide with this atom, and it is going or it has generated two holes. These two that have been generated are also going to be accelerated and are going to collide with some atoms and generate new electron hole pairs. In this direction, we are seeing an electron moving in this direction because it is being repelled by the negative terminal of the applied voltage. And due to the acceleration and to increase in the reverse voltage, it is going to collide against this atom. And as we can see, we have generated these two electrons, and we know electrons and holes are created simultaneously. So this illustrates avalanche breakdown. Please take note. You must be able to illustrate the operation of a Zener diode in the reverse breakdown region. And we are saying a Zener diode, as we have seen, it maintains a constant reverse voltage for a range of reverse currents. And we are identifying the types of currents in this slide. The minimum Zener current is called the Zener current, and for a Zener diode to go into breakdown, the reverse current must be greater than the Zener current, but it must be less than the maximum Zener current. The voltage at which we establish the Zener voltage, we call it is the Zener test current. So IZK stands for Zener current, Zener test current, and Zener maximum current. Please, this is very, very important. We are going to refer to this when we do Zener voltage regulation, because you will discover that if your Zener current is less than Zener current, the Zener diode will not be able to regulate as well as if it is above the maximum Zener current. Don't worry. A look at the three currents or three Zener currents in more detail. What is the maximum Zener current IZM? This is the maximum amount of current the diode can handle without being damaged or destroyed. Please take note that it must not be exceeded. Then the IZT, the Zener test current, is the current level at which the Zener voltage Vz of the Zener diode is measured. And this is an explanation of it, and we are saying our Zener test current is 20 milliamps. Then we looked at Zener current in the previous slide. So please understand the three currents. You must be able to show them on the reverse characteristic curve of a Zener diode and to define them. Please don't confuse Zener current and reverse current. The static reverse current IR is the reverse current through a diode when the reverse voltage is less than the breakdown voltage. Because reverse voltage simply means a voltage or reverse voltage rather across the Zener diode, and it might be mostly we start from 0 and increasing it in the negative direction. But when we go, or when the Zener diode goes into breakdown, or when it starts conducting a lot of current, we say we have reached the Zener breakdown voltage of a Zener diode. Then we have got the Zener power dissipation. This is the power dissipated by a Zener diode, and it is equal to Zener voltage multiplied by Zener current. And the maximum power dissipation is given by Zener voltage Vz times. Please take note, we are now talking of maximum, so we must refer to maximum Zener current IZM as shown. That's the maximum dissipation capability of a Zener diode. Take note of the following points. They are very, very important. We are saying Zener diode is like an ordinary diode, except that it is properly doped so that it has got a sharp breakdown voltage. An ordinary diode doesn't have that. And we are saying also it is always operated in its reverse biased condition. That's the second point. Please, those points must be noted. Then it has got a sharp breakdown voltage, which is called Zener breakdown voltage, or simply Vz. And when forward biased, it just behaves like an ordinary PN junction diode. Then the fifth point, a Zener diode is not immediately bent just because it has entered into breakdown. It is only bent when we have exceeded the maximum Zener current. Some very important points we are continuing. We are saying the Zener voltage remains almost constant as long as the current is between Zener current and maximum Zener current. If we haven't exceeded or gone out of that range, then our Zener voltage will almost be constant as shown by the Zener operating characteristic. Then the Zener voltage, we know it is always specified as we saw at a constant IZT. Then the Zener current will change if you add a load to the output, obvious, because the load will resist the flow of current, or if you change the supply voltage, but output will be almost a constant. Why? Because it is the Zener that absorbs the increase in supply voltage or a decrease in or increase in the load. So we say it must be within, that's the Zener test current, Zener current and maximum Zener current. Then the Zener voltage should be fixed for any current. This is clear. We are now revisiting ideal. You remember your diode circuit models for an ideal and a practical diode. We are doing the same on the Zener diode. This is the symbol of a Zener diode, and it is reverse biased. Why? Because the positive is connected to the cathode and the negative to the anode, and our current flows in this direction. Please take note that it won't flow in this direction. And we are saying we have got Zener current and Zener voltage. We are simply going to represent this symbol by this Zener voltage, and everything remains the same. Zener current remains the same. We simply replace the symbol with the Zener voltage, and these are ideal characteristics. Please take note, the Zener goes into breakdown if and only if the supply voltage, which is V, is greater than Vz. Otherwise, it will not be able to regulate the output voltage. So this is the equivalent circuit. This is the symbol for a Zener, the equivalent circuit. Then these are the ideal characteristic. Please take note that there is zero current flow when the reverse voltage is less than Vz, but we know that there is little current flow. Then there is hardly any increase in the Zener voltage, but we know there is a very small change. These are ideal reverse characteristics of a Zener diode. A comparison of diode equivalent circuit as well as of an ideal diode equivalent circuit as well as a practical diode equivalent circuit. Please take note that we have included the Zener resistance RZ. So this is a practical equivalent circuit of a Zener diode. Vz is maintained, and we are saying there is a voltage across this equivalent circuit. Please take note of our Zener diode symbol. So we are saying when this diode goes into a breakdown, we have got a voltage across it, and this is the polarity of the voltage across this Zener diode. Please take note. Don't say I didn't tell you. Zener voltage as a voltage regulator is what we are going to look at now, and we are saying for it to function as a regulator, it must be connected in this way. This is our V-in unregulated. In other words, this is the output of the filter of the power supply. You remember filters? You must remember. So we are saying the output of the filter circuit, they've got some little ripples, and these are going to be removed by the Zener diode. And how does it do that? Please take note that the current from our power supply is I, and this is going to split into two. IL stands for load current, this stands for Zener current. Please, from your circuit theory, the load RL is connected in parallel with the Zener diode, because why? They've got two common points that are connected together, this point and this point. So we say they are in parallel. Whenever you see a current branching, it means there is a parallelism aspect somewhere, somehow. The voltage across this load is the same as Vz, because the voltage across a parallel circuit is the same. And these are the reverse and forward characteristic of a Zener diode. And please take note of Vz, or the breakdown voltage. So this is our region of operation, and this whole painted thing is what we call the reverse breakdown region. So to achieve voltage regulation, our current through the Zener diode must be greater than Iz min. Iz min is the same as Zener current, Izk, but it must also be less than Iz max. This is all I can say, and there is nothing more to add. So we are saying the voltage across the Zener remains almost equal to Vz when it is operated in the Zener region of the reverse characteristics, which is between or above this and below this. A voltage regulator should keep the load voltage, this is our load voltage V, or constant despite change in the V in unregulated, and also despite change in load current and temperature as well. And we know this resistor is a current limiting resistor. More on Zener voltage regulation, and we are saying, what do we mean by shunt? Shunt simply means in parallel. So we are saying the Zener diode is in parallel with the load. Let's now look at the operation. We are saying the input voltage is unregulated. Of course, we said this is the output of the rectifier filter. Then our resistor is the current limiting resistor, while RL is the load resistor. And we are saying for the Zener diode to act as a voltage regulator, the input voltage must always be greater than the Zener breakdown voltage, VBR. The Zener is reverse biased as shown, and it operates in the region of the reverse characteristics as shown. And what are we saying? We are saying if input voltage is higher than the Zener voltage and our Zener current is between IZ min and IZ max, then the Zener is able to maintain a constant voltage across the output resistor despite changes in V in and IL. This is a very important point. And we are saying the Zener current must not exceed IZ max, otherwise our diode will be damaged. And Zener current must not be less than Zener minimum current or Zener knee current, because the Zener diode cannot operate in the Zener region and will not be able to maintain the output voltage constant. These are important points which must be understood, because why? They will help us to do some calculations from a knowledgeable point of view. We are now looking at how a Zener diode regulates the output voltage with varying input voltage. When input is varying, it means we are maintaining the output current or the load current a constant. We cannot have two variables changing at the same time. So the assumption is RL is constant and input voltage, which is the output of the filter, is varying. Varying simply means it may be increasing or decreasing depending on the input from the power utility. Please take note of the following important points. If RL is constant, it means that load current or the current through RL, which is IL, it is also a constant. And how is it calculated? Because the voltage across the load is the same as the Zener voltage, it means we can simply say Zener voltage divided by RL. Take note that this is very, very important. Since input voltage is changing, it means that also our I, you remember our diagram, our I is changing as well. But how do we calculate I? You must know your potential divider rule. This is the input voltage minus the voltage across the Zener, because the input voltage is the same as the current through the current limiting resistor. So we divide this by this. This is the same as the voltage across this. But we know that I is branching into this plus this, which is Kirchhoff's current law. This point is very, very important, guys. It means that if V in increases, it means that our I is going to increase. But because the Zener is maintaining the output voltage a constant, it means that RL is also constant. So what must be changing? It means that Zener current must be changing. Hence this important point. Naturally, an increase in current results in an increase in IZ. And this can continue harmlessly as long as this is less than IZ max. We are trying to maintain the output voltage constant. So we have made an assumption that when the input increases and the output is constant, which means IL is constant, it means I, which is the supply current, is changing when the input is changing. So it means that when it is increasing, IZ must increase. When it is decreasing, IZ must decrease, as long as the value is between Zener current and this. Please take note. This is the condition that we are analyzing first, whereby we are saying the input voltage is changing. This arrow shows that the input is varying, which means the same as changing. And we have said this is our current limiting resistor IZ and IL. And please take note of this condition, because this is in parallel with this. We are saying V out is equal to VZ. Hence, to calculate load current IL, we can simply say VZ divided by RL. Please take note. It's a very important point. And we are saying this condition, if Vin decreases, it means that our supply current I is going to decrease, and this is going to decrease IZ, because IL must be constant since Vz is a constant. So we are saying the load voltage will be equal to Vz as long as Iz is higher than I Zener current, or minimum Zener current. So we are saying the output voltage will remain constant as long as our current is greater than this but less than this. As long as it goes outside this range, the Zener will not be able to do the voltage regulation function. So we are now we will analyze this later, but please take note that for this condition we are saying we are varying the load, but we are maintaining the input voltage constant, which means that if the input voltage is constant, it means that our I will remain a constant. If this remains a constant, it means that we want to see the way how this how this Zener diode is going to respond if IL increases or decreases. This slide is showing a Zener voltage regulation when the input is varying. If we are saying the input is varying, we are saying it can be increasing or it can be decreasing. So we want to see how the Zener diode is going to achieve the voltage regulation. And we'll start with this. This is a summary, so we are repeating. We are saying the input voltage, which is the output of the filter, can increase. And if it increases, it means that the supply current is going to increase. But we have said that IL is a constant. Why? Because we are saying we are analyzing for a constant load. So it means that our output is a constant because it is equal to Vz divided by RL. So what is going to absorb the increase in I? It means that it is the current in this or through the Zener diode rather that is going to absorb the increase in I. So we are saying Iz increases as Iz is equal to I minus, which is our supply current, minus Zener current. So we are saying this is constant, but this has increased. So what are we saying? We are saying as long as the Zener current is less than the maximum Zener current, the Zener diode operates in this Zener region and is able to carry out the voltage regulation function. So we are saying an increase in I when input voltage increases results in an increase in Iz, but that increase must not exceed this. What happens if our input voltage decreases? This can happen if the voltage from the power utility decreases. So what is the effect? It means that the supply current is going to decrease, but we want to maintain our output voltage a constant. So how is the decrease in I going to be dealt with by the voltage regulator, which is a Zener diode? It means that the Zener diode must decrease, because this, which has remained constant, is equal to this minus this. So we are saying since this must decrease, but it must always be greater than the minimum Zener current, or IZK, so that the diode can operate in this Zener region and therefore maintain the output voltage constant. As long as you've mastered your circuit theory, otherwise your potential divider rule or your Kirchhoff's current law, there is no problem here. We are now going to maintain the input voltage constant and we are varying the load. So what is the effect? Assumption: input voltage is constant and RL is variable. And we are going to analyze two scenarios. RL is going to increase and RL is going to decrease. And we are going to see how the voltage across the output is going to vary. So we are saying if RL increases, because this opposes the flow of current, it means that load current is going to decrease. But we know that the total current I is given by the voltage across the resistor, which is equal to V in minus Vz divided by the resistance of that particular resistor. But we've said the input voltage is constant. It means that I is a constant as well. So this means that if IL decreases, it means that IZ must increase so that I is kept constant. I hope you are following. And we are saying IZ can increase as long as it will not exceed the maximum Zener current. And under such a condition, the output voltage will remain constant. We are going to analyze the second scenario where RL is reduced. It means that if we reduce resistance, we are increasing the current. But we know that I is constant. So if this increases, it means that IZ must decrease. But the output voltage will remain constant as long as this does not go below the minimum Zener current. You remember the characteristic, the reverse characteristic curve of the Zener diode showing the three currents. IZ minimum Zener current is the same as Zener current. And we are saying the output voltage remains constant as long as this Zener current is above minimum Zener current but below this. Let's look at this summary in the next slide. A summary of voltage regulation under varying load. We'll start with an increase in RL, then we'll go to a decrease in RL, and we are going to see how the Zener diode is going to maintain the output voltage constant. If RL increases, it means that this is going to decrease. If this decreases, because I is constant, it means that IZ is going to increase. Hence this statement, hence IZ increases. So we are saying this is going to keep on increasing and must not exceed this, or else the output voltage is not going to be maintained a constant. So we are saying an increase in RL is dealt with by the Zener diode in that the current through the Zener is going to increase but will not exceed maximum Zener current. Therefore, the output voltage is going to be maintained constant. If RL decreases, obviously it means that this is going to increase. If this increases, it means that this must decrease because this is a constant. Hence, an increase in RL causes Zener current to decrease. And we are saying for this is going to decrease. This is going to decrease up to what level if we are to maintain the output voltage constant. And we are saying the output is going to remain constant as long as the decrease of this will not go beyond the minimum Zener current. I think this is clear. We are done with the Zener diodes. Let's go through one or two worked examples. And we are saying calculate the range of the input voltage. In other words, we are saying the input is varying and we have analyzed that scenario. So for which the output will remain constant, and we are given these parameters. Vz, which is the voltage across this Zener diode, is 6.1 volts, meaning the output voltage V out is also 6.1 volts. Minimum Zener current, which is IZK as well, is 2.5 milliamps, and the maximum is 25 milliamps. We are assuming a Zener resistance of 0, and we are given our RL according to our circuit diagram is 1K. So the first thing that we can do is to calculate IL. Since we are given Vz in this condition there, it means that IL is equal to 6.1 volts divided by 1K, which is this value. So we have now found IL. But we are given the minimum Zener current, which means we can calculate I because we are given the minimum. So we want to calculate V in. So when we are calculating V in, we use the minimum Zener current because the output is being held a constant. Please take note that important point. So how do we calculate I? We simply say this which we are given, which is this plus this, we get this. We are now going to use our Kirchhoff's voltage law. So we know that the voltage across this plus the voltage across this give us the minimum, the V in or the input voltage. So in this case, we are starting by calculating minimum V in. So we are saying we are now going to calculate V that we are given is 6.1. So we must calculate V in. And V in is not a problem because we are given R and we have found I. So we are going to say 8.6 milliamps times 2.2. I want you to use your calculator to calculate VR. So if you add that VR plus this 6.1 volts, you get a minimum voltage of 25.02 volts. It's so easy. We now want to calculate because we are calculating range, so we are now going to calculate the maximum maximum input voltage because it is varying. But when we are calculating the maximum input voltage, we use maximum current. So we are given this is there. So we are going to say 25 milliamps, which is this, plus the constant load current, which is 6.3. We are going to find this. So we are now going to calculate the voltage drop across this, and we add it to this because this plus this gives us this. So if we multiply this by this maximum current, we are going to find a certain voltage. Use your calculator to find it. Then we are now going to say the voltage across this 6.1 plus the voltage you get after multiplying maximum Zener current times 2.2. This is going to give you a V in max of 75.52 volts. So calculate the range of input voltage. The range of the input voltage is from 25.02 volts to 74.52 volts. This is so simple, provided you know your circuit theory or your electrical engineering technology. This now, our load is varying, and we still want to maintain the output voltage constant because this output voltage is the one that is fed to our laptops, to our smartphones, to our television. So we don't want it to vary, or else our devices are going to be damaged. So what is the question? Determine the minimum and maximum value of load currents for which the Zener diode will maintain the regulation, which means we must determine the minimum and maximum load currents, and we also must find minimum load resistance. And we are given the following. This Z is equals to 10, which means the voltage across this Zener is equals to 10. We are given an input voltage of 20 volts, which means we can find the voltage across R. And we can simply say, according to Kirchhoff's voltage law, 20 volts minus the voltage across this minus 10 volts must give us a 0. And the voltage across this R is very, very easy to find. We are going to say 20 minus 10 divided by 300. We are going to get 33.33 milliamps. This is your supply current. And this current is going to split into this and this. And we have got two conditions. We want to calculate the minimum load current. So for minimum load current, how do we calculate it? If this is minimum, it means that this is maximum because I is constant, because V in is a constant. So what are we going to do? We are simply going to say the input current is this minus IZ max, which we are given as 25 milliamps. So minimum load current is 8.33 milliamps. To find maximum load current, which is the current across, through RL. It means this must be minimum because this is a constant. So we are going to say maximum load current. To find maximum load current, we simply say I, which we have found to be 33.3 minus this we are given as 5 milliamps. So this is our maximum load current. So we have answered the first part. We are not going to answer the second part. So this is the solution for the first part. Minimum RL, it means load is maximum. So you simply say this is constant. You divide it by the maximum load current, which is this current. So this is the second part. Hope I've tried to explain myself out. And guys, take an electronic devices and circuits textbook and go through any worked example or any questions. And if you find some challenges, I'm there to help you. Effect of temperature on Zener diode. What we are simply saying is the current through the Zener is affected by temperature, and this is clear. We know that an increase in temperature results in generation of thermal charge carriers. So as temperature increases, more current. As temperature reduces, less current. This is clear. Zener diode applications, we have been looking at the voltage regulation element. It is also used in protection circuits. And how does it do that? It keeps the voltage constant to a load. It is also used as clipping circuits. Why? Because it maintains the voltage at a particular value by voltage regulation. You can go on the internet and look for some more applications. Guys, this is our last slide in this Zener diode video presentation. Voltage regulation is the function we were looking at. So it must be able to give schematic symbols, reverse voltage characteristic, forward voltage characteristics, explain voltage regulation when input is varying and when the output is varying as well, do some calculations on voltage regulation. Until then, take care of yourself on your favorite channel, convenient channel that affords you the opportunity at your own pace, place, and time to start by.